the one that I submitted now, I have to make some changes.
It's which one? Are you talking about the circular motion?
Yes.
Here,
That's the last one.
look through there.
Thank you.
Yep.
That is getting closer. But still not. Eight. 5.
Huh? Oh, that sounds weird.
You know, if I put the business be accurate,
Yeah? Okay, I should have put it in recycling. I'll deal with it later. Okay, so. Projector. That. Yeah. Yeah. You already had it from before. I think you had it from, maybe you didn't.
I don't think so.
Is that it? You didn't get that?
No, I didn't.
And I got this. You were here though.
No, I wasn't here.
Okay.
Oh, yeah. DC Day.
Do you have small BC day?
Yeah, oh, I thought you guys were aware of that. No school Monday, right? You know that, right? Thought you knew that. No school Monday. Don't say anything. Like,
You owe me for that entire day. So assuming there's 24 hours in a day, $5 per hour.
okay, so we'll go over page 270. And before I forget, reminder, remember your circular motion, which includes gravity. Test is tomorrow morning. 271 to 8. Number 1, just read it carefully. I'll start on it in a second.
It's just free-space gravitation again, just like calculation.
Yeah, this is a review. This part's a review of some of the gravitational forces to indicate to you that it's similar to Coulomb's law.
Yeah, Coulomb is basically your G and Q is math. You got the six. That just gives it a lot of course times. And the difference here is that you can either pull or push while gravitational.
Well, you guys, this is pretty straightforward. I'll give you the answers to it. I'll go on to Coulomb's law. Save us a little timer. So the answer to 1, that's a negative. So it's a small force. That's why you don't feel it between students. Such a small force indicated by the exponent here. It does exist, but very, very little. 2, force due to gravity. Now we're dealing with larger forces because this is between the Earth and the Moon. That's when the forces become apparent for gravity. This is 2. Okay, for 3, calculate the force between 2 point charges of 4 and a 3 microcoulomb, 2 centimeters apart. Remember to convert to coulombs and meters. That's really the only thing to. This is an electric force indicated by the subscript E. I think they use Q1, Q2. It's fine. You can use Q1, Q2. It says there's a little U in front, so that indicates it's microcoulombs. Which is 10 to the minus 6. That's really the only thing to remember in this problem here. That little funny U is ten to the minus 6. And then centimeters, remember to convert. And that works out to be 270 newtons. For what's the charge on each point? So they're equal charges. So you've got I just put Q squared for equal charges. What is that charge? Just cross multiply. And don't forget to take square root. And you just plug in. Oh, interesting. .4. One times 10 to the negative 1. I better put it, I get confused. Q works out to be 1.9. Coulombs, remember coulombs. 5. Okay, so it's really, these aren't too difficult. So how far apart are they? Solve for R. Cool. Okay, I can do that. I can't even see. 2 times 10 to the minus 6. So this should work out to be 3.6. 0.36 meters. Sure this is being recorded. Yes, it is. 2-point charges. Oh, okay. So this is a little harder. Let's take a look at this. There's different ways of doing it. This is the original force. I'll just simply write that for the original. This is the new force in terms of the old. I'm not done. Okay, so this is the new force, which we don't know. That we don't know. We know this. Okay. And I'm going to okay, so the new distance is 3 times the old. I'm just going to put that here. So R new is 3 times the old. This is the old here. I didn't put any subscript for the old. The new is 3 times, new distance is 3 times the old. So I'm going to erase this in a second, but this is what I would do. I put R new here and then square it. I'm going to erase it in a minute here and put 3R. Oh gosh, I don't need a dog today, please. Okay, so in place of the new distance, I put 3 times the old. And then we'll simplify that further. K, Q, Q. Okay, notice that this is the same as this. That doesn't change. Those values are the same. And then we simplify the denominator to 9r squared. So this becomes my new formula for the new force. This is the old. Okay, this is just a mathematical trick. I'm going to put the new over the old. Yeah, it should be E, fine. Okay, fine. New, and then FE. I don't have to put old. That's the expression for old is just as is above here. Okay, that's what I did on the left. Whatever I do on the left, I've got to do on the right. So on the right, I put K, Q, Q over 9r squared divided by the old. The old is here on the right. K, Q, Q over r squared. Now I can cancel out factors. What's common to top and bottom? This is common to the top. This is common to the bottom. They will cancel each other out. So I just get 1 over 9r squared divided by 1 over r squared. Let's rewrite it here. I don't have a lot of room. Rewrite it here. 1 over 9r squared. Okay. Now I'm dividing by a fraction. So mathematically, that's the same thing as multiplying by the reciprocal. So I can take 1 over 9r squared and multiply by the reciprocal of this. Just means flip it. The r squared goes on top. And that allows me to cancel out the r squared. I get 1 over 9. What's equal to 1 over 9? We've gone all this distance. Let's rewrite it so it's clear. The new over the old. Cross multiply. The new force is 1/9 the old force. (6.2 times 10 to the minus 2). Okay, read 7 to yourself. Yes. Which one? This one? You want that? Sorry. There you go. There you go. Down like here? More? Here you go. Okay, 7. What is the electric? Is the charge on both objects triple? And the distance doubles. Okay, same process. That's the old. This is the new. Charge on both triples. So you instead of Q, you got 3Q. Instead of 3 small q, you got, instead of small q or lowercase q, you got 3 times small q. And the distance doubles. So instead of r, you got 2r. Let's simplify this. You got 9 k q q over 4r squared. Just square everything in the brackets. Okay, that's my new force. I'm going to do the same thing as I did before. I'm going to put the new over the old. Just call it the old FE. Whatever I do on the left, I've got to do on the right. So I've got to put this over this. Okay, so what do I have in common, top and bottom? This on top and this on the bottom. They cancel each other out, leaving you just with 9 over 4. And we're told that the original force, the old force, is 4.4. That works out to be 0.01. Newtons, don't forget the unit. Okay, and then 8. Just read that over to yourself. You want me to scroll down? This one? Let's see here. 9 over 4, what is that? That's 2 1/4, right?
You just round it.
Yeah, just round it.
You round it to 10.
Round it up to 1.0. Okay, number 9. Calculate the magnitude of the net force on the center charge. So let's draw that. Make sure when you're doing these types of problems where you have 3 charges, you get the sign right. That's really important. Get the sign right. Okay, so these are all positive. I made this lowercase on purpose. Later on, it's going to make more sense, but you can keep it uppercase, whatever you want. But okay, so we need to find the net force on this charge here, B, the center. What's the net force? So let's take a look. This is B here. That point represents B. And we need to first of all ask ourselves, what's the force on B due to A? A is positive. B is positive. B is going to feel a push. It's going to be repelled by A. So the force on B due to A is to the right. Okay. Now, what about the force on B due to C? C is a little bit bigger than A, 1.5 times bigger. The force on B due to C. C is positive as well, so it's going to repel. It's going to push B to the left with a greater force than A. It's greater because the charge is greater, but the distance is the same. I can't always guess that. Most of the time you have to do the calculation first, but I can tell just by looking at the size of the charge in C. It's bigger than A, therefore FBC is going to be bigger. Why is that important? Because when I connect these arrows tip to tail, my net force is going to be in the direction of the dominant FBC to the left. That's my net force. Kind of fuzzy. Why is it fuzzy? Anyways, so the equation for the net force will be I just put net. We know it's on B. It's FBC minus FBA, and yes, it's to the left. So we need to calculate each of these. FBC and FBA. Just follow the subscripts. If it's BA, then this doesn't matter the order. Order doesn't matter as long as they're both A and B. I'm just going to put R squared. It's the same distance between all three charges. Okay, so it's QA is 2. And B is 2. Distance is 0.4. Don't forget to square the distance. Okay, that's going to be the smaller force. We expect FBC to be bigger. Should be. Later on, you'll see why I keep on, you don't have to do this, but later on you'll see why I used a lowercase for the center charge. There's a reason for it. It'll help you understand what's coming next. So QC is 3. The distance is the same. So this should be a little bigger, and it is. Carry an extra digit. Instead of 2, I would use 3 if you know you're going to use it in a second calculation. Okay, so now you've got what you need. You've got your FBC, which you need here, and you've got your FBA, which you need here. I'll just rewrite it. So what is that? 1.12. Yeah. 1.1. And yes, I already mentioned it up here, but it's to the left. To the left. Okay. So flip the page to 272. Try number 10 out. We'll go over that together. Try number 10. See if you can get it. These are not in number 10. Remember, I'll just draw them out here. That's your Q1. And this is your Q2. I'm going to call these Q1, Q2. I'm going to use, again, you'll see why later. I'm going to use a lowercase here. You don't have to, but that's your second charge. And then your third charge is somewhere here. That's your Q3. Actually, capital. Capital if it's the source, smaller or lowercase if it's the one that is acted on. If it's a charge that's acted on, it's lowercase. That's what I'm doing. Trying to distinguish what's doing the acting and what's receiving, what's being acted on. Q2 is being acted on. That's why I made it lowercase. So the first step, and just a second point here, they're all positive. The first step is to calculate the forces. So this is what I would do. Here's your clue. This is the force on 2 due to 1. Acting or pushing Q2 to the right. This is the force on 2 due to 3, pushing it up. Those two are going to add tip to tail. It's no longer linear. It's no longer a addition or subtraction. I'll let you figure that out. Yeah.
Just quickly, what is this for? It's like a section.
Those are the ones that I highlighted, the questions that I highlighted on the second review handout for circular motion and gravity.
Okay.
This is a 2 here. Figure out your F21 and your F23. Do that first. Find out what they're equal to. I'm going to give you the answers to F21 and F23. You should be able to do that by now, right? What's the force on 2 due to 1 and the force on 2 due to 3? You're on your phone. iPhone 6? Which one? Android? That's not worth as much. Not worth selling. If it was a 12, I could sell it on eBay. Okay, I'm just going to give you the answer for F21 and F23. I think you know how to do that by now. So let me see here, 3 and 4. F21 is 3 times 10 to the negative 1, 0.3. Whoa. Newtons, it's a force. It's electric force. F23, use Q2 and Q3 in the calculation, and the distance, 0.6. That works out to be a little bit bigger, 0.4 newtons. Okay, so here's the main point. I didn't want to get caught up in the calculations. I wanted to show if it's a two-dimensional case where the vectors, this is a vector. Well, I better do it in a different color. This is a vector. I don't like, come on. That's a vector. That's a vector. Okay? You have vectors that are perpendicular, that are not parallel. You've got to add them tip to tail to form a right angle. This is F21. This is F23. I don't know why red doesn't show up. I'll use yellow for my resultants. Okay, that's my resultant. Or net force. Okay, with an angle. So you need to give me both. Your net force squared is equal to F21 squared plus F23 squared. So F21 is and F23 is I'm going to take the square root. So F net works out to be 0.5 newtons. We're not done. We need an angle. Does it say magnitude? So if they just say magnitude, you're done here. But let's calculate the angle. Let's say the question was, what's the net force? They asked for the magnitude, so this is sufficient. This is enough. But if the question is, what's the net force? You have to go an extra step. What's the angle? So let's do that. Which is just 4/3. So what's that? What'd you get for the angle? Should be greater than 45. What is it? 53. Yeah, thanks, Nora. Yeah, that makes sense. If the question again is magnitude, like I said, sufficient to just give me the answer for the force. If it says what's the net force, you have to go the extra step. Okay, electric field. Electric field, this is just new notes. That's a symbol for electric field. And it has units of newtons per coulomb. And I'll tell you what it is in a minute here, how we get it. Newtons per coulomb. It is a vector indicated by this. It is a vector. Okay. I'm going to remain calm and not get mad. Okay. It has a direction because it's a vector. The direction, and I'll make more sense of this in a second. Let's just define it. This is a definition. Everything is a definition I'm going to tell you about electric field. That means it's a man-made concept. You just have to memorize it. Memorize what it is and how you find the direction. The direction is given by the direction a small positive, this is a key word here, positive. A small positive test charge would move. If you let it go, would move when placed in the field. Okay. Which direction would it move when placed in the cell? This will make more sense visually. It's got to be a positive charge you're testing with. So E, first of all, remind yourself of this. The electric force, this is the way I write it. I write it with the lowercase, big upper and lowercase q, big Q, small q. Okay, the electric force, I'm just looking at the magnitude here, is defined as, it is the electric force. That's what it is, essentially. With the smaller q divided out. This is the source, and you'll see what I mean by that later. This is the source of the electric field. Okay, this is what, if it's a force that we're calculating, this is what's being acted on. The charge being acted on. This is the definition. This works in all cases. That's what it's equal to in general. This is the general equation. Okay, what does it look like visually? So it means this. If you got a, this is a charge that's creating an electric field. It's acting on a smaller charge, Q. Okay, let's say it's a positive charge. And this is a positive charge. Could be positive or negative. We'll deal with negative later. They're both positive. So, what's the electric force? The electric force is just this. K, big Q, small q, divided by r squared. Or that's your R. What's the electric field? The electric field is just this. It's the electric force. It's this without the small q. So what do I mean by that? Write it down. K, Q, small q over r squared divided by, remember what you're going to do? You're going to divide this lowercase q out. So that cancels out. This is your equation. This is your equation for the electric field when you are dealing with a point charge. This is a point charge. Later on, we're going to deal with parallel plates, but this is a point charge. So this is the equation for the electric field. Notice it doesn't contain the small q. The electric field only depends upon the source. Electric field depends only on the source. In terms of charge, I know there's a distance involved as well, but in terms of charge, electric field depends only on the source. The source of what? This is the source. Big Q is the source. And small q is what's being acted on. Small q is being acted on. What's it being acted on by? The source. The source is creating the force and the field. The electric field depends only on the source charge. Big Q. Doesn't depend on small q. Cancels out of the equation. Okay? What about the direction? This is just magnitude I'm talking about here. And yes, I know there's a distance involved. I didn't take that into account. I'm just comparing in terms of charge what's needed to calculate the electric field. You only need big Q. What about the direction? Direction, go back to this diagram. You still need Q, you still need small q, but you don't need it to calculate the magnitude of the electric field. You don't need it to find what the electric field magnitude is. You need this small q to just determine the direction. The small q, if it's a positive test charge, which way would it move in this case? It would move this way, to the right. So the electric field in this case, the direction, I'm just going to remind you of the electric field, always a positive charge. The direction of electric field is the direction. A small, and the key word is positive, test charge. Test because we're just testing the direction. Small positive test charge moves in. When placed, where is it going to be placed? At point P. What's point P? Point P is, this is P here. Point P is here, in that area. It's just, P stands for position. You have to give that position first. And that position P is always a distance R from Q. Okay? Let me just redraw this. Lasso it. Oh, shoot. No. Not now. Let's redo the diagram and change the source to a negative. That's a negative now. Okay. Nothing is really substantially changed in terms of okay, the electric field is still this. It's still K, big Q. It's only dependent on the source over R squared. That hasn't changed. Magnitude is the same. What's changed? The direction of the electric field. The direction is defined, of the electric field is defined as the direction that this is point P here. Point P is here. The direction is the direction that this small q experiences a pull in. Which direction does it experience a pull? Experiences a pull in this direction. It would move in this direction. That's the direction it would move. That's the direction of the electric field. So the electric field, in this case here, the direction of the electric field is to the left at point P. The direction of the electric field due to big Q is to the left. at point P. Obviously, it's at this point P. As opposed to what? One second. As opposed to up above here, the direction of the field is to the right at point P. Yeah, Nora? Oh, I see what you're saying. No, it gets to be, you could say it's negative. It's fine. Just trying to think in terms of all the cases. It's, we don't always draw these charges parallel to the x-axis. So in that case, if you drew the small little q up above, it would be down. But in general, we draw it this way, so you're okay. Yeah, you could put negative.
So for point P, an example,
Yeah,
there's like a big positive and a small positive.
yeah.
If we go towards the left, it would stand right or so.
Which way, you tell me, which way would this small q, lowercase q, which way would it move if placed at that point P there, placed there?
They're opposing each other.
So which way would small q move?
Oh, to the right.
Yeah, to the right. That's the direction of the field.
So, okay, so the field is basically defined by what we're testing with the small.
Yeah. That's why we use the phrase test charge. Okay. Okay, so let's draw the field for each of these. One second. I'm going to draw the field for each of these charges. The negative charge, we'll deal with that first because that's the last one we saw. I'm drawing the field lines. These are the electric field lines. They're like rays of a sun. How many do you draw? As many as you want. It's not exact. The main point is you draw them as rays of the sun. They spread outwards like the rays of the sun. They, what we call, diverge. Okay? So now we've got to draw the direction of the field. Well, we already know the direction here. At point P, the direction was this way. You only have to draw one arrow. I draw two. But that means for each of these lines are called rays, like rays of a sun. For each of these rays, the arrow is drawn towards the negative charge. Why? Because that's the direction a small positive charge would be pulled in. It would be pulled towards the negative source. This is a negative source. What the heck is it? I know. Oh, shoot. I have to charge it. I knew I should have done it last night. That's it. I'm out of energy. Can I?
Pretty sure you can keep it running live.
Like this?
But
I don't think so.
well, if you just die, you'll probably need a bit to start up.
Okay.
Usually what-
Yeah, it's not.
That like an apple.
Oh, maybe you're right. No, it goes for a pretty long time. I just forgot to charge it last night. Oh, you're right. I can do that. Thanks. That's your big Q, right? Okay. Again, I drew these arrows inward. Why? Because a small little positive charge, it's always got to be a positive, small positive charge. It's small so it doesn't affect big Q, doesn't push it out of the way. We're always interested in which direction it would experience a pull or a push. Small positive charge would be attracted inwards, so that's the direction of the field. I'm not finished, Jake. Yeah, so let me do this. Let's look at the case of a positive charge. Change this to positive. I'm going to have to erase a couple of things here. Erase the arrows. That's what I'm going to do. Okay, I joined them. I shouldn't have joined them, but whatever. Which direction would a positive test charge experience? Which way would this charge here move? Would it move towards the positive source? Would it move towards positive big Q or away? It would move away. So each of these, when you draw in the arrowheads, they're pointed away from the source, away from the positive source. This is the source. Whatever creates the field is the source. This is small q. What's the magnitude of it? Just K big Q over R squared. No little q. It's canceled out. Okay. Say something here. No, okay. Shoot. Let's shrink it. Okay, I'm going to draw. This is my negative charge. Let's put a positive charge next to it. Change this to positive. What am I going to have to do to each of these arrows here? This is a positive charge now. Yeah?
Positive charge will go towards the metal for.
Which way? The arrows are towards the source charge for a negative.
Right, yeah.
And for a positive, which way do I draw these arrowheads? Yeah, opposite. Good. Opposite way. Away from the positive source. So, how do they interact, the positive and negative charge? Let's see. The arrows point away from the positive and towards the negative. I'm going to have to draw more in another one here. Oops. Another one here. I'm just adding, they're called field lines. Oh, doesn't work. Adding field lines, just so you get an idea of what the electric force is between a positive and negative charge. I'm going to erase this. I'm going to make these both negative. I don't care anymore. Okay, if they're both negative, the field is towards the source. Okay. And they would repel each other. I'm going to draw in more field lines here. They would repel each other as shown by these field lines. The field lines would not connect. They would spread out away from each other. I'd have to draw more field lines in here as well, but anyways, you get the picture. This one, sorry, I forgot to change it, thanks. This one is negative as well. Two negatives. So the repulsion, obviously they would push apart. They're both negative. Repulsion is indicated by these, they're called field lines. These field lines are not connecting, spreading away from each other. Okay, so you take a break now. You can go on a break. I'm going to charge this. Yeah, you want me to show it or? Huh? From here? I'm going to take a break, so you want to scroll down, you can. 1 sec here. Yeah.